electron arrangements within atoms. In the past episodes, there were a few times that I kept mentioning about electrons. I kept telling everyone, remember, electrons are troublemaker. Electrons decide the chemical behavior of atoms. Now, finally, we're here. We're going to look at the electrons inside atoms. Our goals today, we have two goals today. Number one, find out where electrons are inside an atom. And number two, how the electrons stay there. We may spend majority of the time today to find the answer for question number one. Once we get that answer, to find out how they're staying there will be relatively easier. To accomplish these two goals, we may have to take a tour inside an atom altogether. Before we jump into an atom, take the tour inside an atom, let's take a look of an atom from outside. If I ask you to look at an atom right now in front of you, what do you see? Nothing, of course. It is too small to see. All right, let's assume we have some magnifiers which can help us to see an atom. Now let me tell you what you're going to find out now. What you will see is that an atom in front of you, there is a nucleus there, but outside the nucleus, there are electron clouds. And those electron clouds are divided into layers. We call those layers electron shell, and this is the description of an electron shell. It is a region of space around a nucleus. Those regions contains electrons. Those electrons inside a shell, they have about the same energy, and they spend most of their time about the same distance from the nucleus. You don't see the word approximately very often in the scientific definition or description. Okay, normally scientists don't give you too much room to move away, to move back and forth from the definition of description. However, here they have to put them here because, well, they want you to believe electrons in the same shell, they have the same energy and they're of the same distance from the nucleus. At the same time, they also know that is not true. They don't actually have the same energy, and they may not be of the same distance from the nucleus. Therefore, and there's nothing else better, there's no better way for them to describe this. So they put the two words approximately here. All right, so we see shells in space, and electrons are in those shells moving around. And before we jump into them, let's number the shells. The most inner shell is called shell number 1. Outer it goes from nucleus, they're called shell number 2, 3, 4, and so forth. All right, based on this, I'm going to draw a model of an atom right now. Okay, I'm going to draw a nucleus. I'm going to try to draw, let's say, I don't have enough space. I'm just going to draw 2 shells. Okay, we have a shell, okay, around the nucleus. Okay, so I drew it like this because I know they are not of the same distance to the nucleus. And I'm going to draw another shell. Oh, 2 electron shells. All right. Shells, electrons in shell number 1, they have about the same energy. Electrons in shell number 2, they have about the same energy. However, let's look at something by ourselves. Let's wait, don't just wait until someone tells us what to do. Let's try to figure something out by ourselves. Let's look at 1 electron in shell number 1. I'm going to call electron number 1. Just call it Okay, electron number 1 is an electron in shell number 1 right now. Okay, I'm going to pick an electron from shell number 2. I'm going to call it electron number 2 right now. Okay, I think let's examine these two electrons. First of all, why do these electrons stay here? Why don't they just move away from the atom? I assume all of us can answer that question. The reason that they are staying here is because they are attracted to the nucleus, because nucleus is positively charged. Make sense to you? Okay, if that's the case, let me ask you a question now. Compare between electron number 1 and electron number 2, which one feels more attraction from the nucleus? Of course, electron number 1, we know that electron number 1 is closer to the nucleus, okay? So it feels more attraction from the nucleus. Not only electron number 2 is farther, but also the attraction from nucleus to the electron number 2, this attraction is shielded by the electrons in shell number 1. So electron number 2 will feel less attraction from the nucleus than electron number 1. As a matter of fact, the outer shell electrons always feel less attraction from the nucleus than those from the inner shell electrons. All right, if electron number 2 feels less attraction from the nucleus, then I can claim electron number 2 will have more freedom than electron number 1. Does that make sense to you? Okay, it has more freedom to move around because its movement is less limited by the nucleus, which is true. Okay, electrons in the outer shells, they are more energetic than the electrons in the inner shells. As a matter of fact, electrons in their outermost shell, right now I drew only 2 shells. There may be more outer shells. Electrons in their outermost shell have the highest energy than the inner shell electrons. Make sense to you? Before, well, I kept saying electrons are troublemaker. Now I have to make a new statement. Not all electrons are troublemaker. The electrons in their outermost shell are troublemaker. They decide the behavior of the atom. Remember, electrons in their outermost shell are troublemakers. All right, let's move on. The electrons in inner shell have lower energy. Well, we just figured this one out by ourselves. It makes sense. Inner shell electrons, lower in energy. Outer shell electrons, higher in energy. Electrons in the outermost shell are at the highest energy level. Oh, this is what we don't know. Okay. The outer you go, the more space you have. So the maximum number of electrons can be accommodated by each shell is 2 times n to the power of 2. N is the shell number. Okay. Shell number 1, n equals 1. 2 times 1 squared is 2. So shell number 1 can have 2 electrons. Shell number 2 can have 8 electrons by using 2n squared. Shell number 3 can have 18 electrons. This is the maximum number of electrons each shell can have. It doesn't have to have those many electrons, but that's the capacity of it. All right, we're done. At the outside of the atom, we know electrons stay in shells. Now our job is to capture those electrons. Make sure we know exactly where they are. In order to do that, let's jump into an atom. We go into a shell, try to see if we see electrons in the shell. What are they doing there? Our tour inside an atom is about to start right now. Where do we want to start? Of course, where we see electrons. In the last slide, we were clear that electrons are in the shells. So let's go into the electron shells, try to see where they are exactly in those shells. Now, we're inside a shell, we're inside the electron shell, we look around, we do not see individual electrons. What do we see? We see subshells. Subshells. A subshell is a region of space within a shell. The electrons in the subshell, they have the same energy. Remember, electrons within a shell, they have approximately the same energy. Now, electrons within a subshell, they do have the same energy. That tells you inside a shell, there may be different kinds of subshells. Well, here we go. The number of subshells within a shell is the same as the shell number. So shell number 1 has only one subshell. Shell number 2 will have 2 kinds of subshells. Shell number 3 will have 3 kinds of subshells. Okay, to distinguish of these subshells we see, we use letters to label them. Okay, so far there are 4 different kinds of subshells. They're labeled as S, P, D, F. Okay, from S to F, energy gets higher. The size of the subshells becomes bigger. How do we know the size of subshells getting bigger? Because each subshell, the capacity of each subshell is increasing from S to P to D to F. As a matter of fact, this is their capacity, this is their size. A subshell S can accommodate 2 electrons, P 6, D 10, F 14. Again, these are the number of electrons each subshell can hold. This is their capacity, not how many they will hold. Okay, they can hold less than this, but this is their capacity. Now, there are 4 kinds of subshells. However, those subshells can be found in shell number 1 or number 2 and number 3. How do we distinguish the subshell, let's say subshell P, from shell number 2 or shell number 3? This is how we do it. We use number plus the letter to represent the subshells in different shells. 1s means the subshell S in shell number 1, while shell number 1 only has S subshell. Okay, it doesn't have P. Remember, the kind of subshells a shell have equals the shell number. Shell number 1 has only one subshell, which is S. Shell number 2 will have 2S and 2P. So 2S means the S subshell in shell number 2, 2P, P subshell in shell number 2, 4D will be D subshell in shell number 4. This is how we label the subshells within different shells. A quick summary of what we know so far. We have learned a lot, as a matter of fact. Let's look at what we know so far. Okay, this picture gives us a brief summary. We have electron shells. Assume here is the nucleus. From inner outwards you go, you have shell number 1, 2, 3, 4. Overall, energy is increasing from inside going outside. All right. Then shell number 1 has only one subshell. Shell number 2 has 2 subshells. 3 subshells. Shell number 4 has 4 subshells. The one subshell in shell number 1 is 1s. It has 2 electrons. The 2 subshells in shell number 2 is 2s and 2p. S subshell can have 2 electrons. P subshell can have 6 electrons, and so forth. Overall, again, if you look at each individual subshell, let's look at shell number 3 3 subshells in shell number 3, the energy level is also increasing. Okay. However, don't assume all electrons in shell number 4 are at a higher energy level than the electrons in shell number 3. There are some overlaps in the future. Overall trend is that from inner going outside, overall the energy is increasing. And if you look at within a shell, the energy is increasing. These are all correct. But at some point, there might be some overlapping of the energy levels of different subshells from different shells. We're going to see that later. Let me remind everyone what we're doing right now and where we are. We are trying to take a tour inside an atom, and we're trying to decide where electrons are. Where we are inside a subshell right now. No, we're inside a shell right now. When we look around, we didn't see electrons, we see subshells. So what we will do next, we'll take a tour inside a subshell. Now we jump into the subshell together, look around. We do not see electrons, we see orbitals. An orbital is a region of space within an electron subshell where electron with specific energy is most likely to be found. Oh, finally! From this statement, we know that electrons do not stay in the shell. Electrons do not stay in the subshell. Electrons do stay in orbitals. So this statement tells us right now we're in a subshell, we see orbitals, but it tells us if we jump into an orbital, we will see electrons. Orbitals for electrons is like houses for human beings. You can tell other people you live in a city, you live in a subdivision, blah, blah subdivision. However, the house is the true place you are living in, a specific house. You can say electrons are in a shell, in a subshell. Well, it is the orbital where electrons are staying. The difference between an orbital and a house for human being is that a house can be bigger or small. It can hold different number of people. However, an orbital always, each individual orbital for electrons always can hold up to 2 electrons. All right, if that's the case, let's see if we can fill in these blanks. How many orbitals are there in each different subshell? Remember, we're in a subshell right now. We look around, we see orbitals. How many orbitals are there in each subshell? Subshell S, so far we know subshell S can hold only 2 electrons. We also know that each orbital can hold 2 electrons. That tells us in the subshell S, there's only 1 orbital. Does that make sense to you? If that's the case, we already know that p subshell can hold 6 electrons. Each orbital can hold 2. That tells us in p subshell there are 3 orbitals. D will have 5 orbitals. F will have 7 orbitals. I hope that makes sense to you. A quick summary again. Okay, this is what we have learned about shell, subshell, orbital. Oh, they put the shell in the horizontal way this time. Okay, assume the nucleus is here. So this is shell number 1, shell number 2, shell number 3, shell number 4. In shell number 1, there's only 1 subshell with 1s. In shell number 2, there are 2 subshells, 2s, 2p, 3, 3s, 3p, 3d, 4s, 4p, 4d, 4f. In each subshell, in the case of 1s, there is only 1 orbital. 2s, 1 orbital. 2p, 3 orbitals. 3s, 1 orbital. 3p, 3 orbitals. 3d, 5 orbitals. Then 1, 3, 5, 7 for shell number 4. Now, if we take a closer look at the orbitals, we will see all orbitals have different shapes. Okay, an s orbital looks like a ball, a p orbital looks like a dumbbell, a d orbital has 4 lobes, and f orbital has 8 lobes. Not only that, in the case of p as example, okay, these orbitals, there are 3 p orbitals. Remember that in each subshell, there are 3 p orbitals. And those p orbitals have unique orientation in space. Okay, as in the case of p orbital, the 3 p orbitals are perpendicular to each other. One aligns itself with x, the other with y, the other with z. So 3 p orbitals are perpendicular to each other. Finally, we're here. We found out where electrons are in their orbitals. We also know the shapes of orbitals. We also know something about the orientation of orbitals. Before we move on, there's one job left, is how the electrons are staying in those orbitals. But before that, I'll remind you, try to memorize the shapes of the orbitals, especially the shapes of the S and the P for this class. Okay? You might be asked to draw the orbital shapes of S and P. One last job before we finish the tour inside an atom. We saw electrons now inside the orbitals, but how they're staying there? While they're moving around constantly, we also can find out that they are spinning. Electrons spin. Okay, we use either clockwise or counterclockwise to identify the direction of the electron spin. And we also can find out that if there are 2 electrons within the same orbital, remember an orbital can hold up to 2 electrons. In the case where an orbital does hold 2 electrons, those 2 electrons will take opposite spin. If one spins clockwise, the other will spin counterclockwise. That concludes today's lecture.